Hi, my name is Ricardo, and I'm your host of Math Matters. Today we're going to be discussing the golden ratio and the visual appeal it has. So all the while I'm mentioning the golden ratio and I'm talking about examples of it, I mentioned the visual appeal it has aesthetically to us, mainly. The golden ratio, and I drew the division here, in my previous video I drew it vertically, but this time I drew it horizontally, is defined by this number and is defined by this, division, A divided by B, equals B divided by C, which equals this ratio 5. So the ratio of these segments are equal to each other, where A, the big one, to B is also the ratio of B to C. So this is a kind of unique ratio in a way, but it doesn't intrinsically tell us why it's appealing visually. This definition doesn't intrinsically, tell us why we find it aesthetically pleasing and why we find it so prevalent in society. However, its applications do. And when we discuss its visual appeal, usually we draw a rectangle. So right now I have it in the format of a line, the division itself in a line. But if I extend this into 2 dimensions, we can see this figure more frequently in our everyday life. So I'm going to extend this upwards so we have a more rectangular representation. So the way I do that is I just, let's say I want height B, and the same kind of dimensions on the top. So the point is that the dimensions up here are the same as the dimensions down there, and I can just go ahead and connect that. So now we have this interesting rectangle. So again, if the bottom part is A, the top part should be a length A, and here I've set it up such that B divided by C is phi divided by 1. This is another interesting fact, that because A is defined as the sum of B and C, we can just rewrite A as the sum of B and C. And this makes our ratio look a little more interesting, right? Because if we only use 2 variables, B and C, if we only define it in terms of B and C, which is literally what I made my rectangle out of, B plus C over B equals B over C equals phi. So this is kind of a unique ratio, and it's actually how it's mathematically derived. What do I mean by that? It's how we get from this to that number. And if you want to see a little more about that, you can click on the mathematical derivation video, and I'll show you exactly how this gets you to 1.618. But I must warn you that it is a little more intense on the, I guess, boring just computation of this number. But this is interesting because when we discuss the ratio in this sense, B and C, we have the ratio horizontally, right? And also the height is B in every segment. So we have a square here, a B by B square. This is our B by B square. B by B square. And this is a B by C rectangle. B by C. So this is a B by C rectangle. So this is interesting because the whole rectangle is an A by B. What do I mean by that? It's a length A, so horizontally it has a length of A to its height B. And that is the golden ratio, right? A to B is the golden ratio, so that this rectangle exhibits it that way. And then in this rectangle we have a B to C rectangle, so that's also the golden ratio. So this rectangle that's just formed by extending the golden ratio segment is called the golden rectangle because it has the golden ratio both in the outer rectangle and in the inner rectangle. And that's pretty cool because it just involves the use of squares, right? It's also how later on I'll show you the golden spiral is drawn from the diagonals of this rectangle. And we see this a lot in our society. Now, how does that connect to the mathematics that I've already described here? All this math is kind of cool and interesting, but the way this connects is because this is seen in our architecture, in our art. But why is that? Well, I mean, first of all, when you think it's so prevalent in art and architecture from the Renaissance, even before ancient Greek architecture, a lot of temples have column structures that kind of follow this division of B to C. And this rectangle is very closely followed, where the ratio of the longer length to the height is usually A to B. Now, I mean, this is all approximate and it's never really exact. But it's just because humans themselves, or ourselves, can intrinsically approximate this kind of ratio. And it's a very interesting fact when you think about, well, why is that? It makes a lot of sense that, well, we follow the golden ratio in a lot of ways. Nature around us follows the golden ratio in a lot of ways. And it's not absurd that when you think of what we view as, beautiful or correctly proportioned, it's either a perfect square or a more, length to height wise, base to height wise in a rectangle, disproportionate division that's also equal in two ways. So the big part to this big division, the whole segment of the big division, is also the big division to the small division. And it's just a nice overall division that is displayed in us humanoids. Humanoids, why are we this way? Why is our upper body to our lower body a similar ratio as, let's say, my head to the rest of my torso? It's just a lot of divisions within ourselves follow this, and that's displayed through our art and architecture. And I hope through the next examples I'll show how interesting it is that this visual appeal is seen throughout our art and architecture. Specifically our art. I won't show too much of the architecture because that's a little more complicated and I think boring. The art's really nice, and also the nature and how that connects to this. So throughout all of these, just remember that this is what the visual appeal of the golden ratio means. Essentially, this rectangle and this ratio are central to the visual appeal, and that's essentially how we talk about the golden ratio having aesthetic properties. Hi guys, thank you so much for watching my video. It really does mean a lot. And if you enjoyed this one, I encourage you to watch the next video of my series. And hey, if you're done with the series, there's always more mathematics to learn. Because remember, math matters.